Hello, and welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI generated, and this video is supported by the Norwegian Research Infrastructure Service. This involves collaboration between the universities of Bergen, Oslo, Tromsø, and NTNU, and working with Sigma 2 to manage the national e-infrastructure. In earlier videos, we have used job scripts for parallel computing. In this video, we'll examine more details of scheduling jobs with the Slurm management system. Please note that we will revisit some topics we've covered before, so there will be some repetition. The purpose of Slurm, simple Linux utility for resource management, is to provide a robust, scalable, and efficient way to manage and schedule jobs on clusters in high-performance computing, HPC, environments. We will demonstrate how to execute the Python code mycode on the Fram Linux cluster. We'll start by examining the code using the Emacs editor, but feel free to use any editor of your choice. This code utilizes the OS and time modules. It displays the message "My code is computing" on using a variable named computing and the print function. Although this code is designed to simulate computing, it merely pauses for 5 seconds. Finally, the code executes the Linux hostname command and displays the result in the terminal. Before executing the Python code, we need to load the Python software. First, we clear our software environment to prevent any conflicts by using the module purge command. Next, we load a specific version of Python. We can confirm that the Python software is successfully loaded into our environment by using the module list command. We see that the specific version of Python is listed in my software environment. I am now ready to execute the code interactively via the command prompt. The code indicates that it has carried out computations on the login1 node. However, executing code in this manner on the Fram Linux cluster is not permitted. It is mandatory to include your account number associated with your CPU quota whenever you execute any code on the Fram Linux cluster. The execution we just completed failed to provide any account information to the Linux cluster. To correctly execute the Python code interactively, we must transition from the login node to one of the compute nodes, ensuring we provide our account information. This is achieved using the Slurm command salloc, short for Slurm allocate. I prefer to use a Python setup script for this process. Let's examine this script using the Emacs editor, although you may use any other editor you prefer. This script utilizes the OS module. We use the salloc command to request one compute node. We specify a wall time of 1 minute for the interactive job. To minimize wait time in the Slurm queue, we opt for the development queue. Importantly, the account number is included to authorize this interactive execution. The complete salloc command, along with all its options, is assembled into the setup variable. The script then displays this full command in the terminal before proceeding with execution. You can retrieve your account number using the projects command. In my case, I have 2 account numbers available. Additionally, the cost command provides further details about your account and CPU quota, including how many CPU hours you've utilized and the remaining hours available to you. With the account number provided, we can now execute the Python script. The script will first display the complete salloc command before executing it. Notice the change in the command prompt after running the salloc command. To exit the compute node C8512, we can use the exit command. This will change the command prompt and return you to the login node. You can also use the scalable command directly from your command prompt without utilizing the Python script. However, you will need to remember all the necessary options for the scalable command. Notice the change in the command prompt after executing the command. To obtain information about my interactive job, I use the sq command, short for Slurm queue, with the u option followed by my username. This reveals that my interactive job employs the normal node C8512 and has been active for 31 seconds. We are ready to execute my code on the compute node C8512, where we can observe that the code is actively computing. We have now executed the code correctly by running it on a compute node instead of the login node. After a period, multiple messages populate my terminal, and I am automatically redirected back to the login node without issuing the exit command. This automatic return is due to our setting a wall time of 1 minute for the interactive job, and we have been returned to the login node because the time limit was exceeded. Let's revisit my code. We will increase the duration of the simulated computing to 50 seconds. Next, we plan to execute my code using a job script, so let's examine this script. I am using the Emacs editor, but feel free to use any editor of your choice. You'll recognize many of the same options we used with the scalable command for the interactive job. There's an additional option called job name. This allows you to assign a descriptive name to the job, helping you identify its purpose. For example, the chosen name suggests that my code is computing with parameters c equal to 5 and b equal to 3. The job script also incorporates some crucial error handling options. It's essential to include the module purge command in the job script, preferably with the quiet option. This command is crucial because your current working and software environment are transferred when you execute the job script. Such environments might conflict with the software requirements of your job, and using module purge effectively prevents your current environment from being passed on. Subsequently, we load a specific version of the Python software, which in this case is the same as in my current environment. Nevertheless, we retain the module purge command. The job script executes my code. We are using the echo command to display a Slurm environment variable called Slurm submit dir. This variable is set when the job is initiated and provides information about the directory from which the Slurm job was submitted. We submit the job script to the Slurm queue system using the sbatch command. The job is assigned number 5920794. By using the sq command, we can track this job. The job has the specified name and has been active for 27 seconds on the C8512 node. Later, another sq command confirms that the job has completed. The job script produces a Slurm output file. We verify this by using the "L" command, which shows that the file Slurm 5920794 has been generated. Let's examine this Slurm file using the Emacs editor, although you may use any other editor you prefer. The output from my code remains the same, but now the node number precedes the message, "My code is computing on." This detail is confirmed by the initial sentence in the Slurm output file. The echo command within the job script shows that the script was submitted from my home folder. The job consumed half an hour of CPU time from my quota because it utilized one node with 32 CPU cores for approximately 51 seconds. The Slurm file also notes a queue wait time of about 1 second and a wall time of around 51 seconds. The CPU efficiency is notably low since my code primarily involves a 50-second sleep, and the job script exited normally with an exit code of 0. Although the job was allocated 59 gigabytes of memory, which is the total available on the normal compute nodes, my code uses minimal memory, as it is only simulating computational activity. On the Fram Linux cluster, every user has access to a special work folder on the file system. We can navigate to my work folder using the cd command. Why is the work folder important? It's particularly useful for submitting job scripts to the compute nodes. While it's possible to submit jobs from your home folder, as we've shown, this approach has limitations. For instance, if your job generates a significant amount of data, you might run out of storage in your home folder, causing the job to halt. This issue can be avoided by using the work folder. Moreover, reorganizing your home folder, such as renaming, moving, or deleting files and folders, can disrupt unfinished jobs that were submitted from there. To avoid these complications, it's advisable to submit your jobs from the work folder. To use the scripts and files from these videos as templates for your work, you may copy them from the Saga Linux cluster. First, move to the folder, cluster, work, support, parallel, computing, YouTube. Use the ls command to display its contents. You'll recognize many scripts and files from the videos. We can copy any of these files, but let's try copying the Fortran program mxm to the home folder. Then use the cd command to return to the home folder. Verify the copy with the ll command to confirm that the program is now in the home folder. In our next video, we will provide more details about submitting jobs from the work folder. I am looking forward to the next video, wishing you all happy computing in the meantime.